Welcome to Zero Knowledge. I'm your host, Anna Rose. In this podcast, we will be exploring the latest in zero-knowledge research and the decentralized web, as well as new paradigms that promise to change the way we interact and transact online. This week, Tarun and I chat with Sora and Enrico from Machina.io, a team within the Ethereum Foundation. In this episode, we explore the details of their I.O. implementation work. I.O. stands for indistinguishability obfuscation. It's a type of program obfuscation where, for any two equivalent programs, once obfuscated, would seem the same. They would be indistinguishable from one another. It's very much in the realm of theoretical cryptography today. But as we learn in this episode, Machina is attempting to do some of the early implementation work around this technology. This is our second episode on the topic of I.O. And for a full explanation of what I.O. is, I would recommend listening to the episode with Rachel Lynn. In that episode, we go over what are the theoretical primitives, what are the assumptions, what is the state of the art, what have they tried and decided to move away from, what are they actually moving towards. And I think it gives a more comprehensive definition of what I.O. is. I'll add the link in the show notes to this. In this episode, we dive quite deep into the challenges and opportunities of this cutting-edge privacy cryptography. Our takeaway remains that I.O. is still far from truly practical. However, as with these frontier technologies, having both attempts at implementation alongside the theory can offer interesting insights into how this actually works. Now, before we kick off, I just want to share that we've launched Season 3 of the ZK Whiteboard Sessions. The ZK Whiteboard Sessions are produced by ZK Hack in collaboration with Bain Capital Crypto. This series goes deep on some of the key concepts in ZK. I've added a link in the show notes. Be sure to check out these videos. They are a great way to learn about the fundamentals and techniques powering the ZK systems we often discuss on this show. Also, if you're looking to jump into ZK professionally, or just looking for a new role, I wanted to point you towards the ZK Jobs Board. There you can find job postings from top teams working in ZK. And if you're a team looking to hire, you can also post your job there today. We've heard great things from teams who found their perfect hire through this platform, and we hope it can help you as well. Find out more over at jobsboard.zereknowledge.fm. You can find this on our website, and I've added it to the show notes. Now here is our episode with Sora and Enrico from Machina.io. Today, Tarun and I are here with Sora and Enrico from Machina.io, a team within the Ethereum Foundation. Welcome to the show, Sora and Enrico.
Hi, everyone. Thank you for inviting us to this ZK podcast.
Thanks, Anna, for having us.
Cool. Hey, Tarun, how are you?
Good.
Excited to jump back into I.O.?
Well, somehow I don't know how I became the person who's the co-host on all the I.O. episodes,
guy.
but I guess that's somehow what's happened.
Nice. Yeah, so a few months ago, Tarun, you and I spoke with Rachel Lynn from University of Washington, and in that we discussed the state of theoretical I.O. It was one of my favorite episodes of the year, I think. I think I can say that now. I.O. had been teased on the show for years, but that was the first episode where we actually jumped into it. And in that episode, we discussed how she and her colleagues had in 2021 proved that I.O. was at least theoretically possible if it was built on well-founded assumptions, which they kind of proved in their paper. I very much recommend listening to that one to the audience if you haven't already heard it. Today, I feel like we're switching more into the realm of practical I.O., but I'm putting practical in quotes here because as far as I understand, I.O. isn't usable yet. But I know that's what you guys have been trying to do. So I'm very excited to hear how how it's going, how far you've gotten, what you think is possible, what still needs to be figured out. Yeah, I'm very excited to learn more.
Yeah, okay. So I think as far as we know, or all of the I/O construction we know, including ours, is still far from practical. So for example, even obfuscating some circuit with just 4 input bits still takes more than 6 hours. However, I don't feel we are still in the a dark forest of the practical I/O. Rather than that, we found some of the long but concrete paths toward practical I/O. And we see practical I/O as a concrete technical challenge rather than some a mysterious a dream.
Okay. I would love to get to know both of you before we jump into Machina and the project. So why don't we start with you, Sora? Tell us a bit about what got you excited about I.O. Yeah. When did you start working on this? Were you working on something else before? Like, have you ever done ZK or?
Yeah. So my story with I.O. start from 2021. So exactly from the paper from our Professor Ashjay or Rachel Lee and Mr. Hai about the I.O. construction from standard waveform assumptions.
Yeah.
So it starts from the Wired article a friend of mine shared with me. And this article was exactly about this a paper of I.O. from standard assumptions.
Wait, this was like a Wired article? Is that what you just said?
Yeah, so after this paper was published, I think they are
Wired picked it up.
Yeah, but they became the Wired article, and
oh, cool.
I read that paper, and this was the first time for me to know the concept of the IO. And at that time, I have already worked on some blockchain technologies and some ZKP application developments, and I know some of the concept of using cryptography for smart contracts, like using MPC or FEG. But I felt like if we use such MPC or FEG, this decrease the security of our smart contract applications because you additionally need to write on some ad hoc or threshold committees. But so that's when I learned the concept of IO, I was really surprised and fascinated by IO because it was an ideal solution for enabling smart contracts to process some secrets such that no human can or ever learn, but anyone can use in some predefined logics.
So it's almost like it's the optimal. It's like if it worked, it would be amazing. There would be so much potential. It would actually do a lot of the things that ZK and FHE promised to do, but in better form. But, I mean, did you learn quickly that, it's still a ways off?
Yeah, of course, yes. But, when I read that article, I was really surprised because this universe allows the existence of such secure IO construction. And I thought, I found, a new kind of dream, concrete dream and or goal to achieve, which is, big enough and difficult enough. So this is, how I first met IO.
Nice. So I'd also like to hear from you, Enrico. What's your story? What got you excited about this?
Yeah, I think in my case, I came to know IO more recently. So I think it was around 1 year and a half ago, 2 years ago.
Mm-hmm.
And at the time I was working on an application. I was writing a paper related to multilateral credit set-off, which is a very practical application in which you have an agency that is collecting invoices and IOUs from different businesses, different companies, and they kind of create a network of IOUs after collecting this information.
And you're saying IOUs here, not IO.
Yeah,
right?
yeah.
So
no, it has
clear.
nothing to do with IO at this point.
IOU as in credit.
Yes, exactly. IOU.
Got it.
And since this agency, this single party is able to construct this network, they can then identify cycles of debit and credit, and they can cancel them out from this network. And this yields some liquidity saving for the company. So I think it was a very compelling application for privacy, because I thought that if companies would be basically guaranteed that their personal information wouldn't be revealed to this agency, they would be more encouraged to submit their invoices, and therefore this would yield bigger liquidity savings for the whole system. And I started looking into technology to enable that. And for example, I was working with FHE, but I soon realized that if you want to use FHE, you need somehow you cannot distribute the trust across the whole firms, because let's say you have thousands of firms, you might end up with a very kind of weak system in which just a single firm dropping off the whole process will kind of destroy everything. So what we ended up doing in this paper was just, which is kind of what happens in most of production-ready application today, is they kind of delegate the security of the FHE, the security of the decryption key, to a committee, to a very small committee that is kind of trusted to not collude, to not to not misbehave. I wasn't kind of satisfied by this solution. And this is actually when I already knew that Sora was kind of interested in this I/O thing, even without fully working on that. But we decided to undergo this challenge last year. I think it was exactly 1 year ago at DEF CON. And for me, it was more to kind of a frustration from an application developer point of view.
But it's weird because you were like experimenting with FHE, which is also not quite practical. And instead of going backwards to the things, the libraries that exist, you went further.
Yeah. I think it was too practical for me, so it wasn't satisfying.
Okay. So Machina, I've sort of said this in the intro, that it's a team within the Ethereum Foundation. But like, were you both working already at the Ethereum Foundation? And then you sort of formed this, I don't know, subcommittee. I don't know what it is exactly. But yeah, tell us a little bit about what the connection point is there and what Machina is.
Yeah, so like our Machina IO is like a team or like a project within PSC of the Ethereum Foundation. And we have like worked on PSC even before forming this Machina IO project. So like, this is exactly project we started to research practical IO.
Yeah. But I was kind of curious, like, why IO, why Ethereum? Like, is Ethereum, is it in the roadmap? Is it a part of the plan to explore this stuff? Or is it more just like experimental? You had the green field, and so you decided to explore this.
Yeah, so I think this is more kind of like experimental things. And of course, like IO is not in the official like roadmap published by Ethereum Foundation because IO is still not yet practical. But I think IO is aligned with especially the privacy goal of the Ethereum Foundation, Ethereum. And this is because when we want to protect privacy of applications which involves multiple parties' secrets, data, such as like a private form of the DEX or like some kind of like a mixing applications with like a enhanced security or like a cross-chain breach with Bitcoins, they need to so they cannot be implemented only using ZKP. But in this case, with that IO, we have to rely on either like MPC or TE or like a multi-key FHE and so on.
What do you mean? Like if you have IO, if you want to work with IO, you're actually using these other tech stacks?
Yeah. So like if we have IO, like we can use IO to protect our data such that no one should not be able to know. So for example, if we want to build some cross-chain bridge systems with Bitcoins, like we'll need some system such that these systems uses some Bitcoin private key no one knows for like a signing transaction to withdraw Bitcoin. If and only if a user bans the corresponding wrapped Bitcoin or Ethereum blockchain. But to like manage such a private key and use it only for some like valid cases, we usually need to rely on some MPC or threshold signature or TEs. But if we have IO, we can just make one obfuscated program which hard codes this Bitcoin private key. And if anywhere inputs some ZK proof to say my wrapped Bitcoin is honestly like banned on Ethereum blockchain with some like validated consensus, then this obfuscated circuit will output the signature to withdraw Bitcoin for your address.
Are you talking about replacing existing ZK systems and architectures, or are you saying you're adding IO to some sort of architecture?
Yeah, I think this will replace some of the systems based on like MPC or like threshold-based cryptography, such as threshold signature, MPC, and so on, or maybe some of the TE-based applications.
Your research is about replacing it. It's not about like working with it.
I think actually this is something that we have been discussing very recently, that I think we fit very well with, for example, existing FHE application, and especially, for example, I know that you guys at Zama people as a guest of the podcast, you know that they are building this FHE VM, which is basically an equivalent VM in which all the smart contract states are encrypted under FHE. And in this scenario, I think we can kind of plug into this FHE VM and only replaced the decryption part, actually making the decryption part more secure. So the whole FHEVM, let's say the on-chain logic of an FHEVM remained the same, but the thing that we can actually provide as an add-on with I/O is actually replacing their current system that is handling the decryption part, which similar to what I was describing before, is relying on a committee of people which can always just decide not to cooperate, or even worse, behave maliciously. And we can embed this conditional decryption logic inside an obfuscated program, such that once obfuscated, this can be just released in the public, and everyone can consume this. Everyone can use this program. Everyone can pass ciphertext to this program, and if they are allowed to obtain plain text as a result. But the point is that for this decryption process, there's no longer the reliance on the committee members. So I think this actually kind of fits very nicely with some existing architectures.
So in summary, we can say I/O will replace the trust assumption, in particular threshold assumptions from the existing cryptography-based applications. But at the same time, our I/O will be used combined with other cryptographic techniques, including ZKP and FEG.
Got it.
Maybe a place to kind of go more into the technical details. I think if you think about the original construction that we talked about during the Richelin episode, right, where you have this circuit and you divide it into a public and private bit, and then the private bit is very low degree quadratic, and then the public bit, but potentially large, but still low degree. And then the public bit is unbounded degree, and you kind of separate the calculations with this sort of projecting back into the secret space. Obviously, that is very cool, but obviously there's all this kind of exponential space blow up that can happen as you're doing the computation. To make things practical, of course, you have to effectively choose a different set of assumptions that underlie the security, right? Instead of kind of relying on PRG in degree 2 and things like that, you have to rely on something that's more like linear algebra in LWE. So maybe, I guess, let's talk about the assumptions you're making here. Why LWE, why ring LWE? Obviously that shows up in FHE as well, but just to get an idea of why did you choose the assumptions you chose? And then let's talk about how those enable you to get something more practical. And before we describe the I/O, just more the core assumptions you make, how those assumptions differ from sort of the theoretical constructions and what those assumptions buy you. Because I think that's something that is hard to kind of divine sometimes from these papers, where it's there's a theoretical thing that uses very simple assumptions, but impossible to construct in practice. And there's a practical thing that makes a different assumption, which is not equivalent in many cases, but seems like it should be equivalent. And in the sense that we don't know of any polytime reduction. But yeah, just would love to kind of go down that path with you guys.
So first of all, our I/O construction rely on only lattice assumptions, but not only standard LWE assumptions, but also some two non-standard assumptions. And one of which is actually new assumption we introduced for our I/O construction, called all product LWE.
All product LWE.
So this is our product because we consider a variance of our LWE or instances for corresponding to all of the input patterns. So if you have 3 input bits, we have our 3 input bit, we have 2 power 3 equal 8 patterns of the input bits. And we define LWE kind of different, but a variant of the LWE instances corresponding to each input bit. So in total 8 bits if we have 3 bits. And our assumption claims that even if we rebuild our LWE, such kind of LWE instances for all of the product patterns,
all products, okay,
all of these instances remain random, and there's no kind of relation which breaks the security of such LWE instances.
But you are creating your own assumptions here, so you are differing from the initial, at least for sure, the 2021 work. Are you taking any of their assumptions along with you in these implementations, though?
From 2021 paper, We only took standard LWE assumption.
Okay. And then you added this all product LWE assumption.
Yes. And also, we have also used one more non-linear, non-standard assumption called evasive LWE assumption.
Evasive. Okay.
Yeah, actually, this is also like a super strong assumption. And I think in the last Rachel, I think she mentioned new assumption as a LWE assumption with hints. And she said, recently, some counterexamples against these assumptions have been proposed. And this evasive LWE is exactly one of the such assumption.
Evasive LWE, but is that something that existed outside of this? And you've kind of brought it in?
Evasive LWE is a kind of new assumption. This has been introduced from 2022, and this has been used in many of the lattice-based construction, and we also use that assumption. But I think in the beginning of this year, just right before and after we published the Diamond IO paper, I think there are 4 papers which has proposed counterexamples against this evasive LWE assumption.
Oh no!
Yeah.
So was it like you released some work and then it got broke right away?
Actually, but this is slightly situation is slightly different from usual assumptions, because in most of the assumptions, cryptographic assumptions, these assumptions are falsifiable, which means if you provide some counterexamples, this assumption is basically completely broken. But in the case of evasive LWE, you can consider many variants of this assumption, because it has a lot of variants of the a sampler definition used in the definition of the assumption. And this attacking paper proposes just a counterexample of some specific samplers. So this does not mean this assumption does not fall for all of the cases.
I see.
So we are still not sure if our use of the assumption is secure or not.
But it does sound like you guys are building on, to use Rachel Lynn's metaphor, moving lava. That may or may not hold.
Yes, exactly, yeah.
Got it. Tarun, your question I feel like was broader though. I know we just kind of dug into the actual assumptions here, so.
Yeah, to maybe give a little background. Learning with errors, right, is I take a plain text, I embed it into a lattice with the ciphertext, I add some error, and the goal is that, hey, this linear system, the generator matrix, is not easy to invert. So by adding the error, it becomes too hard to exactly invert. And the hope is that I can add a small amount of error, small in the sense of the noise or the magnitude, and also in the support, the number of coordinates I have to add. And one reason that's very appealing, right, is linear algebra is something we know how to do very easily and do it efficiently everywhere. So for FHE, no stock LWE is more or less sufficient to get pretty far. But for IO, you have to really deal with this idea that at each step, your LWE assumption is sort of implicitly leaking something about the circuit you're using. It's sort of there's some correlation between the way you're constructing the generator matrix and the circuit. And so you have to keep refreshing, and that refreshing is very slow or expensive. This is my heuristic explanation, so you guys can correct me if I'm wrong. It's just I'm trying to simplify as much as I can of what I understand of this. So you have to keep refreshing, and that refreshing is expensive, right? And so you need to find some other shortcut where it's I can apply another LWE transformation, another projection, maybe to a different lattice, whatever, maybe with different error, but something where it looks like it's matrix multiplication, but such that I hope that the matrix multiplication whitens or adds so much noise to the circuit definition without removing the effect of the circuit computation. And so somehow this all product assumption and the evasive assumption effectively do that, right? The hint is sort of a trapdoor to allow you to, kind of in FHE where you project and then denoise, and you can only denoise if you have the secret key. There's sort of some sense in which the hint lets you denoise the real answer if you knew enough information, right? So maybe walk us through those assumptions. How do they map to that? Again, I tried to simplify it a lot. I know it probably misses a lot of the nuance. But yeah, just walk us through that. Just why do you need these assumptions? There's a sense in which there's a gap between FHE and IO, right? That very non-trivial from a complexity theory standpoint. But somehow that also maps into this assumption space. And so I slightly changed my question, but I think hopefully that gives a little more context into it.
Oh, okay, so like your question is like how each assumption is like a necessary or important in the IO constructions, right?
Yeah, I think I just wanted to, I think one really big difference, right, between FHE and IO from just like the standpoint of a user is the circuit has to get obfuscated. So, but somehow that the normal LW is not sufficient. So why do I need these extra assumptions?
I see. So basically, as you said, we need new assumption because while we want to hide most of the secrets about the obfuscated circuit, we also need to reduce or only the circuit output as a plain text in a non-interactive way, so that we have to prepare some like hints which reveals such corresponding output. And we need new assumption to say that this hint does not reveal information beyond what we want to actually reveal to the evaluator of the obfuscated circuit. For example, we need evasive assumption because evasive provides some kind of similar role as a pairing, but it's not necessarily restricted to just a degree to multiplication under some like constraints, because like this plays a similar role to the pairings, but it's not restricted to degree to multiplication. Like a similar technique, or so like a key building block for regarding this evasive assumption is a lattice trapdoor. So if you have some like a LW instance which encodes some like a secret and some like secret data, and if you have like a play image which also encodes another secret, or you can do multiplication between them. And this makes another LW instances which encodes some like a product of these two secrets. And you can do the similar things multiple times. So this like a play image, lattice play image, it was originally proposed to make the kind of multilinear maps. But finally, people found multilinear maps for general use cases based on such techniques are insecure. But evasive rule out some use cases of such play image, lattice play image multiplications, which allows the same type of the attacks against the multilinear maps. In particular, if the products remains pseudo-random for adversaries, this assumption says these like play images will not reveal the internal secrets, and it only reveals the pseudo-random value obtained by multiplications.
I think we rely on a different line of work compared to the 2021 paper that Rachel Lin talked about in the previous episode. And I think the core of our construction of I/O relies on a paper that was published in October last year, which is called Compact Pseudo-Random Functional Encryption, authors AKY. And basically, this paper proposes a new, more algebraic construction of functional encryption. This is also where the evasive LW assumption comes from. And in our work, in the Diamond I/O paper that we published earlier this year, we kind of add, let's say, an additional component to this AKY 24 paper, in which we allow basically a user, an evaluator, let's say a consumer of this obfuscated program, to dynamically add their input bits. And this is where the all product LWE assumption that Sora was describing comes into place. So we are more, let's say, on a different line of work.
Tarun, did that answer your question?
Yeah, I mean, it kind of gets at this, but I guess the real question is just more like, why should I kind of trust that these assumptions will be equivalent, or like at least give me like some comparable amount of security? I think like the other thing I'm a little bit, and maybe this is actually worth going from now the assumption to the implementation, is, I think of a lot of LW things, and it's like I do a single matrix multiplication, I get ciphertext, and then I do apply the circuit, and then I project back for, FHE. But then for I/O, I do something sort of different where I embed the ciphertext, and then I look at the difference between the ciphertext and the true circuit evaluation, and then project that again. And that naturally sort of seems like why you would need this all product thing, right? Because I'm doing two nested LWs. I'm doing an LWE on the raw input, and I'm doing an LW on the difference between the ciphertext and some embedding and the true value. Maybe let's talk through if it's sort of these types of matrix multiplications, why are they so large for a particular circuit? Where does it blow up? Like, is it like nested multiplications blow up really quickly? Is it actually the fact that addition and multiplication blow up the polynomial degree in some more nuanced way? What makes it really large? Like, what makes these matrices large? What makes it kind of slow? And we'll talk about optimizations next. But yeah, just maybe why does it have this reputation of being such a large kind of program for small circuits?
Basically, the main bottleneck we have is that like when you have like a larger input size, you need to prepare more matrices as lattice parameters, and you need like more number of the matrix multiplication to insert each input bit. And this finally like blew up the like accumulated error size, because like initial error is merged by this matrix so that the size of the error increase. But at the same time, we need to ensure that the modulus of the matrix is like sufficiently larger than this like maximum bound of the error. So like finally, like if we have more input size, like we need more modulus, and since modulus is large, each of the matrix size also increases by the increase of this modulus. This is like a main reason that why like obfuscation size, matrix size increases so quickly, even for simple functions.
Everything we're talking about, is it completely theoretical and you guys are making kind of toy implementations, but it's so unusable at this point? Or do you actually see like a glimmer in what you're doing that it could potentially be used?
Yeah, so I actually have in front of me our benchmark results that we shared earlier this year based on this Diamond.io paper that we published. And I think we can definitely say that this is not practical and this is not usable.
Okay.
So we have, for example, as Sora was mentioning, we think in terms of like input bit size, because our construction is basically what allows users, allows evaluator. So again, let's go back, maybe make a step back. And when we talk about obfuscation, we always have these two different phases. One is the obfuscation phase, in which basically the compiler phase, in which you take a program, you pass it through this compiler, and you then get the obfuscated equivalent. And then there's the evaluation phase, in which users, like consumer of an application, will pass their input into this obfuscated program and obtain an output without learning the inner working of this program. And this input size refers to the input size of the evaluator. And for input size of just a few bits, so we test it with 1, 2, 4 bits, a program that is doing, for example, just a bunch of multiplication, like the size of the program is huge, is around 50 gigabytes, and the obfuscation time for 4 bits, for example, is like over 300 minutes, like 5 hours.
Oh, yeah.
So I'm not saying that this is a hint for practicality, but I think one interesting observation that we see is that actually there's this huge asymmetry between the obfuscation phase and the evaluation phase. So the obfuscation phase, for example, in the case of the 4-bit input size, took around 5 hours, but the evaluation took only, let's say, 18 minutes. So, and the cool thing is that the obfuscation is something that needs to be done only once. So we can potentially admit that this takes a long time. And what we really want to optimize for in order to make it practical is the evaluation phase. So I think, our implementation at least gave some numbers. They put some numbers into something that everyone says, yeah, it's very inefficient, but they didn't have the numbers. So I think this is a good point to start. And we also have a lot of idea, and we also have a lot of, let's say, we have a rather clear roadmap in order to make it practical.
Actually, one kind of interesting question that maybe this brings up, this like asymmetry, is like, I think about ZK, how ZK went from like very impractical because like everyone wanted to, until kind of like 2012 Gentry paper, like everyone was like, we have to do a PCP, versus like, then people were like, okay, find a way to write a constraint set that's small. And then in that constraint set, all the polynomials are small. So then you can kind of like, optimize things, before we got to Grot 16. It sort of seems like you need a step like that where you find some like lower dimensional reduction that like allows you to embed how you describe the circuit efficiently. But there's also a question of like pipelining, like can I separate? Is there like any ability to parallelize some of the obfuscation versus evaluation components such that they can kind of like run in tandem? So I'm just kind of curious, like what are kind of optimizations you see that are possible and like which things are impossible, which things will not work? Because I do think like that for ZK, right? It's like in theory, people could have made really inefficient implementations of ZK in the 90s, but then it just took kind of like 20 years to find like the right representation such that things were small, and then it was like off to the races towards optimization. And that's not to take away from like all of the things like lookups and whatever that obviously made things faster, but I do really feel like it was like changing how people thought about representing the circuit that changed things. So like how do you foresee that for IO? How do you think about optimization and within IO?
Okay, so I will take my favorite, let's say, optimization potential, but then I will also let Sora add his opinion. Like for me, is actually I would make an analogy closer to like the FHE space rather than the ZK space, which is when Gentry introduced the bootstrapping technique in FHE that allow basically to, let's say, allow computation for like unbounded circuits. And I think this is also the case for I/O, or in general, it's not strictly for I/O, but it's more for, let's say, the underlying primitive that we're using for I/O is something called BGG encoding, which actually one of the G is actually Gentry and the B is Dambonnet. And this was a construction that was published over more than 10 years ago for attribute-based encryption, and is still the main building block for this whole category of non-interactive cryptography that, for example, involves also witness encryption, functional encryption, and I/O. And we actually need a way to do noise refreshing, a sort of like a bootstrapping on this BGG encoding that would allow, similar to what Sora was mentioning before, to increase the input bit size such that, for example, we add some input bits, then the error blows up, but we are able to do this noise refreshing to kind of move the error back to zero and keep doing it again without having to, let's say, allow from the very beginning this error space to handle this gigantic input size, because this wouldn't be practical. So I think this is one way, one promising optimization. And we know that actually Richard Lin published a paper last year on bootstrapping, which I think it proves a theoretical point that you can do bootstrapping on BGG encoding, but I think it's not practical yet. So maybe we need a more practical way to do bootstrapping on BGG encoding, and I think this would kind of bring us closer to practicality.
Actually, I do think a kind of important part about at least what I understand of your construction is actually disencoding, which seems like you take a bunch of small matrices to select which input bits are needed and then evaluate, then add noise. So maybe walk us through what the encoding is and like what the difficulties are, because I do think there's some nuance to that that's unique to your construction that like, you know, the other IO papers don't kind of cover as much. So it would be great to kind of understand how the selector matrices work.
Yeah. So like a sector means a selection for each input bit, right?
Yeah, I just mean like, the small.
Okay.
Yeah.
Yeah. So like actually this is like new technique we introduced, and the selection means that so you can first imagine that, like, if we have encoding which involves both of the encryption of the obfuscated circuit and your input bits, you can do the similar technique to the functional encryption proposed in the compact random functional encryption paper to evaluate this private circuit on your input and only recover the plaintext of the circuit output. And we use this section idea to insert or evaluate input bits to this like encoding, which only contains the obfuscated circuit. And this section means that you first have the encodings, which does not have any of the input bits, which contains only obfuscated circuit, but you can also access to the play image matrix, each of which correspond to, like, for example, you have two matrices for first input bit. One is corresponding to input bit 0, and the second one is corresponding to input bit 1. And if your first input bit is 0, you choose the 0th one and multiply this matrix. Then you can insert your input bit 0 to the given encoding. And the obfuscator provides such matrix for each input index so that evaluator will choose one of the two matrices for each input index to insert each of the evaluator's input bit one by one. And finally, they can obtain the encoding which contains both the obfuscated circuit and all of the evaluator's input bit.
So one thing I think I was kind of curious about is the choice in which, the permutation in which you evaluate the order of the input sequencing can change the embedding, right? But then you add this Gaussian noise, which is invariant to the permutation. So I'm kind of curious, is the ordering of the input bit constructions part of the obfuscation, or does it actually not matter because in distribution it's equivalent once you re-add the noise at the end? Because that was sort of my thing. I think about a lot of obfuscation methods that are draw a random secret permutation and permute, right? Is that involved in the security here or?
So in our case, in our construction, I don't think we involve some of the kind of random permutation matrix, because this selection part only depends on the evaluator's input bit. So we don't need to randomly permutate such orders.
Oh, I see. Okay.
Maybe you may think, is it IO candidates proposed probably in 2015 or 2018? These things will converts your circuit to the branching problem, and which is permutation matrices, and obfuscate each of the matrices. Yeah, I understand.
Yeah, I sort of was reading this and thinking Barrington's theorem, that, exactly that.
I see.
And that was, but because when someone is introducing a new set of assumptions, right, it changes the tools you use to prove the same. You have two different assumptions. You're trying to prove basically a similar or same security property, that something isn't corruptible or it's indistinguishable against other adversaries. So, but because there's one set of proof techniques in the theoretical construction, another set in the practical construction, understanding where they are similar and different is kind of important. So that's sort of the lens in which I'm asking this.
The high-level idea of our security proof is that first, when we use evasive LW, we have to prove that all patterns of the product between the LW instances and all of the provided lattice preimage remains pseudo-random. And in your case, a part of the lattice preimage corresponds to the matrix which insert some input bit, each of the input bit and a secret corresponding to each input bit to the given encoding. To prove that these preimages will not make our initial encoding insecure, revealing some secret, we consider two paths n LW instances such that we try all of the multiplication patterns of the n preimages where n is the input size. We have to prove that combinations of all of the two path L instances remain pseudo-random. And actually, we finally need to rely on our OR product LW to finally claim that these of the instances remain pseudo-random. And the essence of the OR product LW is that if we just reuse the same secret, but with changing some a public port, it's easy to attack these LW instances and easy to distinguish between the two of the LW instances with some random words. So the play condition for evasive LW will not hold. But our assumption introduced in our product LW is that if we insert input depend or secrets between the initial secret path and the public port, then it might be possible to say these LW instances will be looks independent and pseudo-random. So for example, let's say the initial secret is just S, and we prepare some secret corresponding to the bit 0 for the first input bit, and bit 1 for the first input bit, and also S, and another two secrets corresponding to 0 and 1 for second input bit. And the public part will be different for every input pairs, 0, 0 or 0, 1, 1, 0, and 1, 1. And we will like review the encoding, which depends on 4 patterns. So first pattern corresponding to input bits 0, 0 will involve some common secret times secret for bit 0 at the first input bit, and bit secret for bit 0 at the second input bit, and the public matrix corresponding to 0, 0. And we do the same things for 0, 1, 1, 0, 1, 1. And we finally right on our assumption to say that all of these 4 patterns will be pseudo lambda, so that the play condition to use this evasive LDP assumption will hold. And finally, we can say that the initial encoding along with these lattice images, each of which holds each of the secret piece of the secret, will remain the pseudo lambda.
I do think it's actually it's interesting, right? Because like here you care about this, like, I think like the oversimplified by a long shot and dumbest version of IO is like, I take a Boolean function that has some Boolean expansion, and then I take the set of circuits that describe that function up to some constraint, and then I randomly sample one of those circuits and evaluate it partially. And that is sort of not at all obvious that like the sequence level thing is equivalent to that sort of like very high level view of like how people think of IO. So if we zoom out a little bit, I actually think another kind of important question, this is a question I think that's still open in every field from sort of like ZK all the way to AI in different ways, which is like, what is the correct set of benchmarks for IO? Like, what programs should we think about as like, this is a good benchmark that we should be targeting, right? That like, oh, like given this benchmark, as we do optimizations, we're improving performance or whatever on that. I think for ZK, like for better or worse, in the beginning, all the benchmarks were this like Fibonacci stuff. But then eventually, once people had VMs, they started like targeting real programs. And, for AI, obviously, they have like, there's obviously all this fight over like what evals are correct. So in a world where IO becomes practical, like what are the programs you think that are the benchmarks? What are the benchmarks you're doing now? Like, you talked about, you gave wall clock times. Well, that had to have been for some circuit. So like what circuit were you using? And
Yeah. I think actually we have a pretty clear answer to this because in this future there are, I kind of hinted to before, in which the whole application logic is run by an FHE processor, and only the decryption logic, the conditional decryption logic is handled by an obfuscated program. Well, in this world, actually, we only need to obfuscate a single program, and we only need to obfuscate this program once, and then this can handle all this private computation application forever. So really what we need to obfuscate is not, I think this is also a common misconception when it comes to IO, that for each application that you want to, let's say, have some privacy, or you want to hide secrets, you need to obfuscate a specific program. But actually, and this is also another paper from Gentry, GGH 13, in which introduced this concept of, maybe it didn't call it this way, but we call it like universal IO. So as long as we are able to obfuscate this program, we can kind of handle the security of any type of application, really. And the logic of this program is as follows. So it should take as input a snarks, a proof, together with a ciphertext, and there's some verification logic that is encoded in the obfuscated program that will, let's say, in a kind of a very simple words, is saying, am I allowed to decrypt this ciphertext? And this will be based, for example, on some on-chain smart contract logic. And if the verification passes, the decryption proceeds. So it's like I think we can simplify the program as snark verification plus FHE decryption. And as soon as we get to obfuscate this program, we are basically, let's say, done.
You just have to do that.
Yes.
So I also have like another answer about how to benchmark IO, especially for more short term. So I think more concrete way for benchmarks in short term is obfuscating a circuit with, for example, 32 input bits or more. Because if input bits is like I think more than 16 or like 18, it's basically impossible in practice to prepare some like a function as a like a truth table. So like if we can make practical obfuscation for input size like 32 bits, this is like a non-trivial result such that we cannot do the same things without I/O in a practical way unless P is equal to LV.
Yeah, so actually that's a very salient point because like to me another kind of, again, I'm oversimplifying in all these descriptions, but mainly just so because like I do think like I/O, if you haven't spent a lot of time trying to understand the assumptions, can be kind of confusing. Is I/O is very good at taking anything that has a really large gap between the average case complexity of an instance and the worst case complexity of an instance, and it makes everything the worst case complexity, right? So it's like, take these SAT problems where like the worst case SAT problem is like very hard exponential time to find an answer, but the average case is like very low degree polynomial. I/O in those problems has to convert the low degree thing to like close to exponential or at least super polynomial, right? And so I guess the natural question is like there are a bunch of problems like that are natural. The SAT is a little bit annoying, probably, I imagine, as your benchmark. But you could imagine other benchmarks that are like the simplex algorithm, like in optimization, where like it's well known what the worst case instances are. And you basically can run like an average instance, which is known to be fast, versus the worst case instance and show that it's like the same sort of reduction. Another question that's sort of related to this is the power of I/O, and at least from my perspective, is the fact that it's sort of universal in the sense that you can reduce it to, if you have it as a black box, you can like construct all the other cryptographic primitives you want, functional encryption, FHE, ZK, whatever, right? Like all of them are sort of like, this is the big boss. And if you solve the big boss, all of them are sort of corollaries without that much work, right? And so I'm curious how you think about benchmarking the reductions. Like, if I/O was sort of a universal compute, you had a computer that had a universal I/O thing that was fast. How do I benchmark how good the I/O is on how well it does at implementing the reductions to these applications? Because I actually think like the reductions are in some sense the more practical use case, right, than raw I/O itself. Or that was more a question. Sorry.
Reduction means like reduction. So like using I/O for more like simpler applications.
Yeah, exactly. Like all of kind of the known, like, hey, these are known cryptographic applications that if you had I/O as a black box, you could implement quickly or like implement efficiently.
Yeah.
Like,
I see.
what are those benchmarks? Because I feel like those are like the practical applications that people want, right, to some extent.
I see. So yeah, I understand like at least for cryptographers, like this like a reduction to the like using I/O as a black box to make like a simpler applications or like extend like a symmetric key encryption to public key encryption can be like one good applications. But I'm not sure if this is like how we eventually use I/O for like practical applications because yeah, I believe even if we can make ZK or FHE by I/O, like direct construction of them should be more practical than I/O reduction. And at the same time, I think, as Enrico said, we will use I/O part only for some specific small parts, like doing conditional decryption, so that I'm not sure if, like, for example, measuring benchmark of like a I/O-based FHE construction or I/O-based ZKP construction makes sense if our like a wide range of the I/O, which also rely on ZK and FHE, is like used for this benchmark.
I was just curious, like, have you tried implementing any of these reductions? Like,
No, because at this time we can support only a few input bits.
Okay, yeah, fair. I mean, I'm curious, like, while you're writing the software here, like, what gates do you use as your unit tests? Like, is it just like add and multiply for 3-bit integers, or like, are you like doing something? Yeah, kind of curious. Like, where do you start when you're doing a project like this?
Yeah, I think like most of the circuits are really just, for example, multiplying a polynomial by a secret bit. So we have a known polynomial and our secret is either a 0 bit or like a 1 bit, and we want just to make sure that the output is what we expect. So it's not really any meaningful program that we are testing out, but it's just some really dummy program that is testing out the functionality that we describe in our paper. I think also something that is worth mentioning is that, before I referred to this BGG encoding as the core building block for our construction. And again, we are not trying to reinvent the wheel here. There are like known libraries, for example, like OpenFHC library, which is a very popular C++ library, already had all the primitives that we needed to handle this BGG encoding. And they tried in the past some sort of, let's say, similar construction to I/O, and therefore that's how they build this. But it's also very similar to like what all the FHC people, all the, let's say, lattice people are more familiar with. So I think what we also want to convince people is that the jump from FHC to I/O is not like a huge jump. Like most of the idea, the concept, and the actual code that we are using is also shared across these two domains.
In the I/O construction level, we only evaluated some dummy circuits, as Enrico explained. But after publishing our I/O implementation, instead of focusing on directly or improving the efficiency of our I/O construction, we are focusing on improving the efficiency of this encoding layer. Because this encoding has not been researched to make them really practical, in similar to ZKP or FHC. And they are researched mainly in the theoretical area. So we first need to make this encoding practical. And for this encoding layer, we try to implement our FHC evaluation over encodings. In particular, doing some multiplication, some nonlinear operation over large modules and so on. And we introduce lookup table evaluation over this encoding to make them more practical. But we still have some challenges to make them concretely efficient.
Oh, interesting. You're actually using lookup tables.
So after making our I/O implementation, we next focused on making a lookup table evaluation over this encoding. Because when we see the history of the ZKP or FHC, lookup table evaluation played a significant role to make them practical. So we considered if we can make the similar native lookup evaluation technique for this encoding so that we can do nonlinear operations more efficiently. And we actually make such ideas, and we confirmed the efficiency has been improved, but we need more improvements in the case of this business process encodings.
I have just a quick clarification question about something that was said 20 minutes ago. You mentioned the Gentry paper of 2012. Tarun, I think you had actually mentioned that.
Oh.
But I always think of Gentry as FHE, but you used it in the context of ZK,
I mean,
so now I'm confused.
A lot of ZK stuff, he's just done stuff and everything. So
okay, it is actually Gentry ZK.
Yeah. There's an old paper of his that arguably Grot16 probably owes a lot of the original framing from. Grot16 made this paper practical, but from a theoretical standpoint, I think he figured out the right representation or encoding that made it efficient. So
I see.
There's this but he's done something in everything. The best part about Gentry is he wasn't even trying to be a cryptographer. He was a lawyer for 10 years before.
Amazing. Yeah. Do you know his story?
Yeah, his story is pretty crazy.
We met at ZK Summit 13. He popped over, and I definitely pitched him to come on the show, and I hope I get to invite him sometime. I think it would be a lot of fun to have him on. But yeah, I think his background's amazing. But I actually didn't realize that. I always thought of him very much in the FHE world. But that's cool. I do want to say one other thing before we sign off. I just want to say a quick shout out to one of your colleagues, Pia Park, who kind of brought us together. I had reached out to her. She, I think, had published something through the Machina project, and then she introduced me to the two of you. I'm just curious, what was her work there? And just since she did that intro.
Yeah, actually, we met with Pia at a residency that we did earlier this year in Taiwan. And I actually already had a chance to work with Pia before because she audited one of the projects that I was working on in the past. And it was very actually fun because probably in 2 days, I think I'm not wrong saying that, after 2 days that she spoke to us for the first time and learned about I/O, she was already contributing to the repo. So we already had, probably she's still the main contributor, and she was definitely the main driving force at the very early stage in which we were kind of building this from scratch. And Yeah, I think actually all the results that we mentioned before are really thanks to Pia and her work on the engineering side, and especially the Rust side of our library.
Nice. How big is the group that's contributing, actually? Is it two of you and then Pia was part of it, or is it bigger than that? Is it open source and there's lots of people that are kind of adding?
Yeah, I know. I think so. The main group is me, Sora, and Pia. But I think a big shout out, as I mentioned before, is on the OpenFHE guys, which like our whole library relies on, and which we kind of, let's say, we relied a lot on them on like trying to understand how this PGG thing work, and also on the optimization side. But we are also very welcome to have new contributors, and we probably should also be more active on the documentation and on the communication side to make it easier for other developers to jump into that. But I think what I want to make sure that passes as a message from this podcast is that, I/O sounds this kind of crazy thing that is inaccessible, but is literally just, a jump from something that already exists. So if you already have some skill in lattices and in FHE, I think that the jump is not too long. You will be very, very equipped with everything you need to start contributing and to start helping us optimizing this BGG encoding that we spoke a lot about.
This is a very left field question, but you mentioned it's sort of, you've said this throughout the episode that lattices are kind of at the heart of this. Does this make I/O post-quantum secure? Or is it one part is lattices, but actually there's all sorts of cryptography that could be broken?
Yeah, I think as long as this security assumption that we added are secure, and as long as the learning with error assumption is not broken, I think we can claim that I/O is also quantum safe. Yes.
Okay.
I think I should mention that, at this time, as far as we know, we only have a I/O construction from standard assumption, which is not post-quantum, because these kind of things, all of the standard assumption constructions rely on bilinear maps, pairings. There are many proposals of lattice-based I/O constructions. But all of them rely on some kind of new lattice assumption. So yeah, as Enrico says, if these new lattice assumptions are really secure both against classical and quantum adversaries, we can say we will eventually have post-quantum I/O potentially.
Sort of. Answer kind of, sort of, depending.
Yeah.
Okay.
Yeah.
Got it. I want to say thank you to both of you for coming on, sharing the story of Machina I/O and your interest in I/O, the work you're doing to implement it, where we're at in practical I/O. Yeah, thanks so much.
Yeah, thank you very much.
Thanks, Anna. Thanks, Tarun.
Good to be here. Thanks for coming on.
I want to say thank you to the podcast team, Rachel, Henrik, Tanya, and Hector, and to our listeners. Thanks for listening.